So the last talk of this session is on characterizing universal reconfigurability of modular pivoting robots by Hugo Akitaya, Eric Demain, André Gongxi, Dylan Hendrickson, Adam Herschterberg, Matthias Korman, Oliver Quarter, Jason Lynch, Irene Parada, and Vera Sacristan. And the talk is given by André Gongxi, who is a student, so he's eligible for the best student presentation. So you can start.
Thank you. Hi, my name is Andrew Gongxi, and I'm going to be talking about pivoting modular robots. And if you were at the business meeting, you might remember that there was one paper with 10 authors. This is the one, so a lot of pressure. This is joint work with Hugo, Eric, Dylan, Adam, Maddie, Oliver, Jason, Irene, and Vera. And I know a lot of people in the audience have definitely seen Big Hero 6, but for those of you who haven't, sorry, I didn't maximize. The main character is doing this robotics project, and he has a lot of little robots, and I'm just going to show you a little scene from the movie, just a few seconds. See those robots there on the right? Beautiful, they turn into a hand. And that's sort of what we're trying to do. Of course, a little simpler, but the main idea is the same. Modular robots are simply these small unit robots that don't look very impressive on their own, but when you put them together, they can build amazing tools and beautiful shapes. And I drew sausage out here for you guys using some square robots. And in our case, we're going to be looking at robots that attach by edge, facet. Except since we're considering 2D space, it means edge. The problem is hard enough as is anyway. That's why we're also mostly looking at 2D for now. 2D space also helps us sort of restrict the kind of shapes that we're looking at. And specifically, we're of course going to be trying to tile the entire space. So we want either squares or hexagons. Another one of the requirements that we've got is that the robots are aligned to the lattice. And that has more to do with the fact that the properties of the robots and how they move are, they're pivoting. So you need them aligned. Otherwise, pivoting becomes a little problematic. The other main requirement we have is just connectivity. We call it single backbone. Basically, we want the robots to be connected at all times. We don't want disconnected components. And that's what we're going to be calling a configuration. It's just a connected set of these modular robots. On the bottom, I have 3 examples. On the left, we have a valid configuration. You can see everything is nice and connected. In the middle, we have an invalid one since the configuration is disconnected. So technically, that's just 2 configurations. And on the right, we have another invalid one since the robots aren't aligned with the lattice. Finally, I just want to mention that the robots are interchangeable. They're not in any way labeled. It doesn't matter where they go. Each one is sort of basically the same. And before I go to this, I just want to show you a little bit of a demo as to the fact that, look, these robots actually exist and they're really cool. Look, I have a little video of the robots actually pivoting and moving around each other. And sure, these are in 3D, but obviously we can apply this in 2D as well. I just wanted to show you this extra little move. Beautiful. Now let's look at the problem we're looking at. That's simply reconfiguration. The input is, of course, 2 connected configurations on the same number of robots. And we're asking the question, is there a sequence of moves that transforms one into the other? I have an example here where I go from a 6 to a 9 by moving one robot at a time, pivoting them around. This begs the question, what kinds of moves are we going to be talking about? And since we're specifically working on pivoting moves, I'm just going to show you. It's not very complicated. In general, the main idea is that one module, sorry, I might use module and robot interchangeably, I mean the same thing, simply pivots around some shared corner. And we have, in the case of squares, 3 kinds of moves. The restricted move, which just pivots around a corner, the leapfrog move that pivots around a corner until it hits another edge, and finally the monkey move, where you pivot around a corner and attach to another corner. And I have a little bit of an animation here for you guys to see all the moves. See, everything's pivoting, everything is nice and aligned. In the case of hexagons, we still have the restricted and the monkey moves, but of course the leapfrog move just doesn't apply because of the geometry of the shape itself. There's the animations for the two moves. Great, great. As a little bit more of a motivation, I want to talk about some previous results. There's a lot of results in other kinds of moves, but I'm just going to stick to pivots. And specifically in the cases of both squares and hexagons where we only have the restricted move, remember the simple one, it's actually always possible to reconfigure as long as we forbid certain patterns. You can see here on the bottom the 3 forbidden patterns in the cases of the squares and 1 in hexagons. And what this really means is that even a single appearance of any one of these in the entire configuration makes the problem hard. Another interesting result is that when we only have the squares with a restricted move, it's actually always possible to do as long as we have a few extra robots that we can sort of just drop on the external boundary, and then we can play around with those, make bridges. It's interesting, but let's focus on what we're doing, and we're trying to do universal reconfigurability. So no forbidden patterns, no extra modules. So I'm just going to show you our results. The table is pretty easy to read. The lines are the types of robots we have, whereas each extra column adds an extra move. The first column is just the restricted move, then we add the leapfrog, and then finally we have access to all of them. So first, some lower bounds, and in fact, most of the settings are, well, p-space hard, so really hard to do. But as soon as we add the monkey move with the hexagons, aha, we can do it. And we have an n-cubed algorithm that I'm going to focus on for most of this talk. So let's jump straight into it. Remember the setting again. We have these hexagonal robots with these two kinds of moves. We want to go from one configuration to another by just pivoting. And the main idea will be we're going to try to go through a canonical configuration. In our case, this is going to simply be a vertical path starting at the topmost module in the initial configuration. I have this drawn here on the right. It's simply going to look like a nice straight path. And I just want to mention one simple thing about this. We're sort of going to just forget about the stick once we start building it up. So modules that are part of it, we're just going to consider them removed, and then we just, do the same thing, just induction of a smaller problem. The problem, our algorithm has 3 main steps. And the first one is actually the easiest one, technically. It's removing degree 1 vertices. There's a bit of subtlety to it, but in general, by simply pivoting around, more often than not, the robots will be able to find a position where they're touching 2 robots. So there might be some exceptions, but I don't really want to go into the details of that, because I think steps 2 and 3 are more interesting. And specifically, step 2, I think, is the essence of this, and it's increasing connectivity. What do I mean by that? The initial configuration, of course, we know is connected, it's given, but our goal will be to make it 2 connected. And as a quick review, a 2 connected component is simply one where removing any single node maintains connectivity. Of course, what I mean by this graph is I'm just talking about the underlying adjacency, edge adjacency graph of the modules. And I have an example here on the bottom. Notice on the left, the configuration is not 2 connected because, of course, most of the robots are actually cut vertices, right? But if we take this robot here that's dotted and pivot it into the dotted position, all of a sudden the configuration is connected, and notice that none of the robots are now cut vertices. Finally, I want to mention a little bit about the intuition as to why we're doing this. And the way to think about it is that once you have a 2 connected configuration, that means that the external boundary is basically a cycle. So we know that some of the convex corners will be able to move, which is great because we're going to be able to move them all the way up, right? But I do want to go a little bit more into detail here. And remember, we're talking about the edge adjacency of the robots. And I want you to consider the block tree of the graph. All I really mean by that is look at maximal 2 connected components. So for instance, on the left here, notice that each one of the purple connected components is actually a 2 connected component, with the gray ones being little paths in between. And the trick to making the entire configuration 2 connected will be to merge the leaves using these bridges that we're going to do. And the analysis of this is that every single merge can take at most order n squared moves. So for every node of the block tree, we're going to be merging it into a different block. And since it's n squared moves per merge, there's at most n nodes. Of course, that's where the n cubed comes from. I also have an example here at the bottom where you can notice that this southwesternmost block leaf, if we take the two southwesternmost robots and pivot them around into these two positions, we get the configuration on the right, where notice we have now gotten rid of one of the leaves of the block tree, decreased the size by 1, and eventually we'll get to a two-connected configuration. Great. So that means that I can show you a little video. I'm just going to show you steps 1 and 2 put together. And remember, step 1 is just going to remove the 1 degree vertices. First, I'm just going to do that one at a time. I randomly picked them, started pivoting until they find a position where they're not 1 degree anymore. And now we have no more degree 1 vertices. So let's look at what step 2 will do. We take this node in the block tree, and we start sort of pivoting what in the paper we call the crew around until we attach to something else. Do the same here. Boom. Two-connected configuration. Beautiful. And steps 1 and 2 are done. So let's look at step 3. Remember, we reached step 3 with a two-connected configuration that has no degree 1 vertices. Now what we're going to do is we're going to be freeing and removing the robots. Remember how I initially said that what we want is to have a robot that can move all the way to the top? Well, actually, instead of that, what we're going to do is we're going to free a robot in such a way that it is what we call two-free. And all that means is that once we remove that robot, the configuration stays two-connected. And of course, this is because we don't want to redo two-connectivity because of the n-cubed running time. I have an example here on the bottom left. Notice that the dotted robot is not what we would call two-free, since removing it would, of course, break two connectivity. We'd have a lot of few cut vertices in here. So our goal will be to create these two-free robots on the outer shell. And how we do this is by simply shrinking the configuration, sort of taking empty spaces that are inside and bubbling them towards the outside. In the example I have, notice that the dotted position is actually the reason why the dotted robot is not two-free. If we can somehow fill this position, we can move the robot. And that's exactly what we're going to be doing. And with a few careful local moves, by moving this out of the way and starting to move other things up, this is what we'll end up getting. And now notice that the dotted robot is indeed two-free. We can move it up into the stick, and we're going to continue with this new two-connected configuration that has no degree 1 vertices and repeat step 3. And that's all there's to it. So basically the main idea is steps 1, 2, and 3 do the following. Step 1 removes degree 1 vertices. Step 2, two-connected configuration. And then of course step 3 will simply turn everything into a stick. And that's our algorithm. Since I only have a couple of minutes left, I wanted to talk a little bit about lower bounds as well. I want to specifically look at what happens in the same setting when we simply remove the monkey jump. So remember, setting's the same, restricted move, but no monkey jump this time. And what we're going to be doing is, of course, reducing. We're going to reduce from a motion planning reachability problem. And all you really have to know about this problem is that the goal is to see if we can get from one point in a graph to another where the nodes of the graph are these gadgets with different states depending on how they're traversed. And really the only gadget we're going to be caring about is what we call the locking 2 toggle. And this locking 2 toggle has 3 states. The main idea behind it is that you can think of it as having 2 unidirectional tunnels. But as soon as you traverse one tunnel, all you can do is go back along that same tunnel. So it sort of flips the direction of how you can traverse that tunnel and blocks the other one. You can see an example here on the right. The agent traverses the gadget downwards on the left. And then, of course, that means that this tunnel is now locked and can only go back. Finally, the last thing I want to show you is how we simulate this in our setting. The important part is that the module is actually, the agent is actually 2 modules. And I don't even know what to tell you guys about this one, but the important part is that the locking configuration comes from this sort of, you can think of it as a vertical connectivity. You can see that these red robots, C and D, maintain this connectivity. If we remove both of them, we'd break it. So it's sort of, the locking behavior comes from the fact that only one of C and D can move away at a time. So as soon as we move this robot out to let the agent sort of enter the gadget, the other red robot is blocked, and now the other side cannot be traversed. And I can also show you the traversal real quick. We're sort of using either this almost disconnected or this almost disconnected component. And then, of course, just on the bottom, the same thing happens, and we have left the gadget. Notice now that if the agent came in again along this wire or any of the other wires, in fact, none of them can be traversed. Finally, as a quick summary, this is a first universal reconfiguration algorithm with no restrictions or adding any robots, and we've also characterized all the other modules as p-space hard. Some future work would be improving the algorithm. The running time is n cubed, but our lower bound is n squared, so there's a little bit of a discrepancy there. And another interesting question would be, how about moving robots in parallel to minimize some sort of a make-span function? Finally, for other models, can we reduce the number of forbidden configurations or find some other global properties that will help us? And thank you. That's it. I'm going to take questions now.
Okay, so let's thank the speaker. And are there any questions?